Hey guys, this is Professor Janacek, and I want to go over some examples of area under a curve. I'm going to look at some basic conceptual type problems. So example 1 here, I'm taking the integral from 2 to 4 of 2x plus 3 dx. Notice I have taken that integrand 2x plus 3, and that is my function, and we have the graph of that just from 2 to 4. So I'm just going from 2 to 4 on this, and if I were to look at this, what's underneath that curve, it looks like I have a trapezoid, and so that's what I'm going to try to find the area of. Just that section there. So the area of a trapezoid is 1/2 times a plus b times h. A and b are the two bases, and h is the height. In this particular situation, I am going to look at my height going from 2 to 4. Oops, that's the height. Notice I'm thinking of this trapezoid kind of on its side. Base A, I'll have the left-hand side, and base B will be the right-hand side. So when we determine this area, we get 1/2 times A, which is 7, plus B, which is 11, times the height, which is 2. Put all that together, and it looks like we have 18 for the area. Let's take a look at example 2. We're going to integrate from 1 to 6 of 2x plus 6 dx. Notice again my integrand is my function, and I'm going to graph that. So I'm going to look at the graph y equal to 2x minus 6. I've already graphed that here. It is also a line like example 1. Notice I have only graphed it from 1 to 6. So I'm only going from 1 to 6. If I look at the shapes that this graph makes with the x-axis, it looks like I've got two triangles here. So I'm going to have to find the area of each of these triangles. So here we're looking at triangles. The area, of course, is 1/2 base times height. Now I will consider this as two separate triangles and then add them together. Let's take a look at the one on the left-hand side. I'll call that triangle 1, so it has area 1. Its area 1/2 base, I'll say its base is, what is that, 2, and its height, notice its height is a -4. Yes, that's going down to -4, so I have to remember that as a negative value. That gives us -4 for the area of triangle 1. Triangle 2 is the one on the right. Its area also 1/2 base times height. The base here looks like it is 1, 2, 3 units over, and then its height is 6. So this area we end up getting 9. So the area of this entire triangle in this situation is area 1 plus area 2, -4 plus 9, which gives us 5. Now, yes, it is possible in some situations that you would want to find the overall area, not looking at the one below the x-axis as a negative value and the one above as a positive, both of them as positive values. Context clues should help you identify what you're looking for if you want to consider these all as positive areas or if you need to consider some as negatives. All right, on to example 3. We're going to integrate from 3 to 4 of the square root of 1 minus the quantity x minus 3 squared dx. So we are simply going to look from 3 to 4. All right, we're just going to go from 3 to 4, but let's take a look at that function. So our integrand is the square root of 1 minus the quantity x minus 3 squared. Well, I'm going to go ahead and kind of clean this up a bit. If I square both sides and then move the x values to the left along with the y values, what we end up with is x minus 3 squared plus y squared is equal to 1. Now this should be somewhat familiar to you. This is a circle and it is centered at 3, 0, and it has a radius of 1. Again, I'm getting all of that from this equation, x minus 3 quantity squared plus y squared is equal to 1. Okay, well, I know the area of a circle. Actually, let's go ahead and plot that circle. So let's see, we have center is 0. I'm sorry, the center is 3, 0 right there. I'm going to go 1 in every direction. So back 1, to the right 1, up 1 even. And it gives us something like that. Now you'll notice what we have here is a semicircle, but I'm only integrating from 3 to 4, which means we just go for this little bit here. So notice I'm not finding the area of the entire semicircle, just a quarter of the semicircle. So we just want, instead of the circle, we want half. Let's see, so the circle, we said its area we know is pi r squared. We want half the area of a semicircle. So half of a semicircle, well, that's half of a half. So the area is 1/4 pi r squared. Well, for this particular example, we know that the radius is 1. So that gives us an area of pi over 4. Well, isn't that nice? I do want to take a look at this example using the definition. If you recall, the definition of the definite integral, which gives us the area under a curve from a to b of f of x dx, is actually the limit as n goes to infinity of the sum, k goes from 1 to n, of f of x sub k star times delta x. This is the limit of the Riemann sum, also known as a definite integral, and this will give us the area under the curve. Now, along with this definition, we need to know that delta x back here is easily defined by b minus a over n, and the x sub k stars will use the midpoint, so it's going to be a plus k minus a half times delta x. So looking at this, in this case we have a is 3, b is 4. Again, this is still example 3. My function f of x is this crazy thing, square root of 1 minus the quantity x minus 3 squared. So what about delta x? Well, b minus a over n, 4 minus 3 over n gives us 1 over n. And x sub k star, if we're choosing the midpoint for every one of those intervals, that gives us 3 plus k minus 1/2 times delta x, which we've already decided is 1 over n. Oh, that simplifies just a wee bit to 3 plus k over n minus 1 over 2n. So in order to determine this integral from 3 to 4, the square root of 1 minus x minus 3 quantity squared dx, we're going to take the limit as n goes to infinity of the sum, k goes from 1 to n, of f of x sub k star, that's 3 plus k over n minus 1 over 2n, and then multiply that by delta x, or 1 over n, which would be the limit as n goes to infinity of the sum, k goes from 1 to n, of, now all I'm going to do is evaluate this function f of my x of k star. So I'm going to put this bit inside into the function. Oh yay! Doesn't this look like fun? That's the square root of 3, oh wait, no. It's the square root of 1 minus the quantity. We have our x's, that's 3 plus k over n minus 1 over 2n. Subtract 3 from that, and then square it, and then multiply all of this by delta x, which is 1 over n. Oh my gosh. There's gotta be a better way. It is possible we could do this, but it's not going to be pretty. Fortunately, we have something called the fundamental theorem of calculus, which will help us out in just this sort of situation. That, however, is in another video. So for now, enjoy!